Hello, everyone. Hello, everyone. We're the Self-Driving Vehicle project. Our team consists of undergraduates, mostly ECE, and also some high schoolers as well. We'd like to introduce two cars. So even though we have one project, we have two cars. Our first car, Rascal, it uses, oh, well, we'll explain it later, but yeah, okay. There you go.
So for the first car, Rascal, it was designed to imitate a real car's motion and turn like a real car. So if you can see in this diagram, the inside wheel turns less, so it travels less distance and goes at a steeper angle. And to have our car imitate this motion without skidding, we have an Ackerman steering system and a differential gear system. So the Ackerman steering is in the top right. You can see it moves so that the wheel that is on the inside turns at a steeper angle than the one on the outside. And the differential gear system, which is here, it has a series of 90-degree gears that allow the friction from the car's wheels to change the motion so that one axle and its respective wheel turns at a different speed than the other one, so that there is no skidding in our car.
All right, so real quick before I talk about the software, the goal of the car is to be able to imitate a real car, and so to be able to a real autonomous car, and so to be able to do that, we need to have a machine learning model that can learn off of the example. And so, like going into that, there's two main parts of our software architecture, which is written in Python and runs in the ROS or Robot Operating System environment. And so what this allows us to do is any of the nodes that are in blue, those are different nodes, which is like a separate process that runs independent of each other, and they communicate through different topics. And what this allows us to do is it allows us to have more modularity and make sure that each part of the code works with its own part or with its own like goal, and we can interchange different parts. So for example, you might see over here, we have the simulator and the main. So for example, main is like what runs on the actual car, and it communicates with like the hardware, like the motor and the servo. But we can run, instead, we can swap that node out to run with a simulator. And that allows us to be able to work on parts of the code without having the actual car. And this is really important for our development. But on the left, the main part, which we'll get into, is that on the left, you'll see that there is that is the part that deals with the machine learning, and the part on the right is pure pursuit, and we'll go more into detail about that soon.
So as Brennan just explained, we curated a web display for our project, and it has many different features. So on the top right, you can see it has the ability to plot different points. So the robot, when we were testing it, could go to just different points and record it for our training data we needed for our machine learning model. And over there, we have different commands to have these features like add points, delete points. And for our data visualization, we created custom graphs based on the data that are coming in from the ROS. And as you can see, example is a sign value of one of the values we were looking at to see our and analyze our data. And you can do it for any, and for these graphs, you can do it for anything you want, because the data is gonna be coming in at millisecond range from robot operating system. Then we're displaying it via JavaScript to the user.
So we wanted to have a way to draw paths for the robot to follow. So you see in the back, we have an intersection over there. So we made a model of the intersection on the web display, so we can draw paths on the web display for the car to follow. And to do that, we created a pure pursuit algorithm, which basically uses the car's position to self-adjust to stay on the path. And to get the car's position, we had to use odometry. So for that, we use the IMU to get the angle and the encoder to get the distance. So based on those two values, we can do math to figure out where the car is in order for the car to follow the path accurately.
So for the self-driving aspect of the car, we wanted to create an end-to-end imitation learning model. And so the idea of the model is it would mimic the pure pursuit algorithm, or either one of us like controlling the car. with a controller. And so the way the model works is we take image frames from the camera feed and it outputs a speed and curve value, which is sent to main or our controller of the car.
What you see on the bottom here is actually the output of all the convolutional layers of the model. And what a convolutional layer does is if you look over there at this graph with the grid, what happens is you slide a kernel, which is the green box, over the image, which is the box with all the ones and zeros, and you get an output which represents how much that point in the image represents that feature. And that's how we allow the model to recognize parts of the image.
Now moving on to our second car. Our second car is Scamp, and it's a path following car. It's going to be used to go and just it's going to follow a path, and that path is going to be based off a city car in a city intersection. And this will be used to go and train our other autonomous car to recognize traffic or other cars that are moving. Some of its features, it uses a mechanism drive. So instead of the front two wheels turning, all the wheels are stuck straight in place, but they have rollers on them. And this means that if they move in different directions, it allows it to have like a larger range of motion. So it could slide like perfectly sideways or spin in place, which a normal car wouldn't be able to do. And then we also have documentation so that we could replicate both cars. So in the future, they could go and create more cars and test more advanced traffic scenarios.
Okay, so I can go into how the data flow in our pathfinding car goes. So down here, we have a teensy microcontroller, which basically controls all of the hardware. So like the IMU and the motors. And then communicating to the microcontroller is a Jetson Nano, which is basically like a full-on computer that runs Linux. And we're running ROS on that, and it communicates to the teensy through serial. And then the Jetson Nano also runs the Flash server, which we highlighted earlier. So for the future, right now we don't have a way to orient the car. It's only like relative to itself instead of the environment. So we're planning on implementing SLAM so that it can do that. And we also we want to work on path extraction from video, so we can take a video of a car in the intersection and replicate it on the car.
And as for Rascal, so far we were able to get the peer pursuit to work pretty well, but we were not able to get the machine learning model to do more complicated stuff, like be able to choose left or right at an intersection. So far we were just trying to get it to work on just driving in a loop by itself.